So, today we are going to look at two examples on vibrations of one dimensional elastic structures that we have started with strings. So, today we are going to look at axial vibrations of bars and torsional vibrations of circular bars. So, let us begin with axial vibrations of bars. So, where do we find bars in axial vibrations? So, some examples are in an ultrasonic machine. So, in an ultrasonic machine, what you have is a bar which is shaped like this, which is connected to an actuator. So, this bar is called a horn of the ultrasonic machine, and this is an ultrasonic generator which passes ultrasonic waves in this bar, and because of this shape you have large amplitude motions at this workpiece. So, such a machine is used for machining brittle materials, for example. Then you find bars in axial vibrations in pneumatic hammers. Sometimes also known as jackhammers. So, in a jackhammer, which looks roughly like this. So, these are used for drilling or chipping operations in construction sites. So, here you have a bar which is also in axial vibrations. Then you have piezo actuators, sensors, in which you find a bar which made of piezoelectric material, which is under axial vibrations. Then in various structural elements, you may find bars in axial vibrations. Now, in order to model the dynamics of bars in axial vibrations, we begin with some assumptions that we make on this modeling. So, the first assumption that we make is that all points of the bar are in all points on a cross section have same motion. So, what I mean by this is, suppose you have a bar at a certain cross section, all points will have the same motion. The second assumption that we make is that the strains strain is small. So that we do not have nonlinear effects. We are going to discuss only linear vibrations of bars. The third assumption is that there is no transverse motion of the bar. So, this bar, the material points are vibrating only along the axis of the bar. There is no transverse motion. And the fourth assumption or that we make is that the material of this bar is linear, homogeneous and isotropic. So, with these four assumptions, we are going to now look into the equation of motion of a bar in axial vibration. So, let me draw a bar . So, this bar is made of a material of density say rho, has an area of cross section A, which may be a function of the spatial coordinate x, has Young's modulus E and has a length L. Now, at any location x of the bar, the displacement of the cross section in the axial direction is measured by this field variable u as a function of x and time t. Now, we are going to derive the equation of motion of this bar using the Newtonian approach. So, what we will do is we will consider an infinitesimal a small section of this bar as I have shown here, and draw its free body diagram. So, we will consider the stress. So, this element is of length delta x, lies between x and x plus delta x. So, the stress on the right face I will write as sigma x plus delta x comma t, and on the left face this sigma x comma t. Let this area be A x plus delta x and this is A x. Now, we are going to write the equation of motion using Newton's second law for this this small element. So, the mass of this little piece may be written as rho times A is mass per unit length, and the length of this little element is delta x. So, this is the mass of this element. This mass times the acceleration in the longitudinal direction, that is the double derivative of the field variable u with respect to time, that must be equal to the forces in the longitudinal direction. So, the force on the right face is given by sigma times A on the right face minus the force on the left face which is given by sigma times A on the left face. Now, if I divide this whole equation by delta x and take the limit delta x tends to 0, then that would imply rho A times the acceleration is equal to the partial derivative of sigma into A. Now, we require to represent this stress in terms of the displacement, the field variable. So, in order to do that, we will need two things. The first is the material constitutive relation. Which will relate the stress with the strain. So, we know that the axial stress is proportional to the strain and the proportionality constant is the Young's modulus. So, this is the Hooke's law in one dimension. Along with this, we need the strain displacement relation. So, which reads epsilon, the strain is del u del x. So, if I substitute this expression in the constitutive relation and put this back in the equation of motion, what I obtain on rearrangement of terms so this is therefore the equation of motion for axial vibrations of a bar. Now, remember that this equation has been derived by considering a small element of the bar that in no way tells us or describes to us the full physical picture of the bar. So, what I am trying to get at is we need to complete this description of this bar in axial vibrations, we need the boundary conditions. Now, as we have discussed before, these boundary conditions are of two types: geometric and natural. Now, let us look at some examples and identify the boundary conditions. So, we begin with a uniform bar So, the equation of motion in this case simplifies to this equation. Because the area is now constant, it is no longer a function of x. So, it can come out of the partial derivative, and this can be simplified further to obtain this equation of motion for a uniform bar. Now, the boundary conditions of this bar. as you can see, this end of the bar is completely fixed at the wall. So, at x equal to 0, there cannot be any axial motion of the bar. Now, this boundary condition is fixed by the geometry of the problem. So, this is a geometric boundary condition. Now, this end is free. Free would mean that there is no axial force at this on this face of the bar. Now, force, as you know, force here on any cross section is given by sigma times A. So, at x equal to L, the axial force must be 0. Now, we have used the Hooke's law and the strain displacement relation previously to obtain this relation between the displacement and the stress. So, therefore, these two will imply E times A del u del x, this computed or evaluated at x equal to L must be 0. Since A is uniform, so the boundary condition turns out to be this. Now, this comes from a force condition. Such a boundary condition is a natural boundary condition. So, we finally have the equation of motion of a uniform bar and the boundary conditions, which completes the description of this fixed free bar in axial vibrations. Next, we look at another example. So, this is a bar at the end of which this is a fixed bar at the end of which an oscillator is attached in this manner. So, this is a point mass attached with a spring of stiffness K. So, the displacement of this mass from the equilibrium position is measured by this coordinate y. So, let us first write down the equations of motion for this system. Now, here you have, as you can see, a bar and this mass. So, you have the field variable which measures the displacement of the bar, the material points of the bar, and we have this coordinate y which measures the displacement of this mass, discrete mass m. So, the equation of motion of this bar remains the same as before. So, we can write now, for this oscillator which is connected at this end, we can easily write the equation of motion as m y double dot plus k times y is equal to k times the displacement of the bar at this end. This equation can be easily derived if you write down, if you take the oscillator separately and write down its equation of motion. Now, these are the equations of motion for this system. So, as you can see, they are coupled. Now, let us look at the conditions at the boundary. So, at this end of the bar, it is completely fixed. Therefore, we can easily write the displacement is 0 at this end. On the other hand, at this end of the bar where this oscillator is attached, we can expect an interaction force with the oscillator from the oscillator. So, we have already written the force on any cross section as E times area del u del x at x equal to L at time t. So, that is the force. Had there been no oscillator, it would have been 0. Now, since there is an oscillator, you can write the force that this absorber or this oscillator puts on this end, which is easily obtained as k times y, which is the motion of this point, minus the displacement of the bar at this end. So, this is the boundary condition at this end of the bar. So, here we have a geometric boundary condition, whereas on the right end we have a natural boundary condition. So, with these two examples, we will move on to the next example or the next case that we are going to consider, which is torsional vibrations. So, we are going to consider the case of torsional vibrations of circular bars only. So, where do we find torsional vibrations of bars? So, mostly in rotating machinery. So, you have shafts in rotating machinery. Which transmit torque. Such shafts are subjected to torsional vibrations. For example, in turbines, in rotors, in crankshafts, in turbines, crankshafts of engines, in the dentist's drill, so in a dentist's drill you have a wire which is under torsion. These are called drill strings. They are also found in petroleum excavation and mining industries. So, these shafts, for example, in a mine like this, so this is the drilling head, and here you have a shaft which transmits the torque to this drill head. This shaft is under torsional vibrations. It also has some amount of transverse vibrations, but the torsional vibrations are quite dominant in such situations. These are called drill strings. So, in such situations you find shafts or circular bars in torsional vibrations. So, once again, for the mathematical model of such a bar, we make some assumptions. So, the first assumption that we make is that we have already said that the bar is circular. So, we are going to study only torsional vibrations of circular bars. That is to ensure that there is no warping of the cross section. We will assume that the strains are small, so that the dynamics can be adequately described by a linear model. And we will also assume that there is no transverse motion. There is no transverse motion of the bar. So, with these assumptions, let us look at a circular bar. So, here I have a circular bar made of a material of density say rho, as an area of cross section which may be a function of the spatial coordinate x. The shear modulus or the modulus of rigidity is represented by G, and this has a length L. Now, at any location x, the field variable that measures the torsion in the bar the local torsional displacement of the bar is represented by this phi x comma t. So, at any location x at any time t, this is the torsional displacement of any cross section. Once again, we are going to derive the equation of motion of such a bar in torsional vibrations using the Newtonian approach. So, we are going to consider a small portion of this bar between the spatial coordinates x and x plus delta x. Now, on the right end of this bar, let us consider the moment represented by m x plus delta x at time t. On the left hand, we have the moment on the cross section as m x comma t. Now, inside this little element, we are going to consider a ring of certain radius r. So, I will draw this portion, this ring separately. Now, consider in the undeformed ring, two axial lines like this and the corresponding radial lines here. Now, this little element, when the bar is under torsion, there will be a differential rotation between the left face and the right face. So, because of this differential rotation, this red element, which is somewhat like a rectangular element, is going to take up this configuration. So, if you look at this angle, that is the small rotation, the differential rotation between this face, the left face and the right face. On the other hand, if you look at this angle, this is nothing but the shear strain experienced by this initially undeformed red element. Now, this shear strain is a function of the radial position of this element. So, if I draw these two elements once again, so this was the red element which was before the deformation. This is the green element after deformation. So, this is the shear strain in this element. So, with this kinematics, we can write r, the radius of, so this is the radial location. So, we can write r times delta phi, which is this small length, r times delta phi must be equal to this length, which is delta x times the shear strain. So, that would imply, upon taking delta x tends to 0, which I can also write as so this equation that we have obtained from the kinematics of this torsional deformation that of the bar, we can now relate the shear strain at any radius r at any time t in terms of our field variable, which is phi. Of course, this is also a function of x, because phi is a function of x. Now, we are going to use this kinematic relation further. So, let us look at the constitutive relation of the material. So, we know from Hooke's law that the shear stress is proportional to the shear strain. So, the shear stress is G times the shear strain. So, if I use the kinematic relation in this expression, I have the expression of the shear stress at any radius r, at any location x, at any time t. So, once I have the shear stress, I can integrate this, multiply this with the area and integrate, multiply this shear stress with this area and integrate over the whole face to get the moment, the torque in the bar. So, m at any location x at any time t, I can write from the shear stress times the small area of this ring and the arm. So, arm times this shear force. So, that will give us the moment, the torque. Now, if you integrate this over the full face, then you get the total torque on this face of the bar. So, if I substitute this expression, I have this, and since these two terms, the g and phi, they have nothing to do with this integral of the area. So, I can safely bring them out, and this therefore is the torque. And we know, we can easily identify this integral as the polar moment of the area. So, now I have related the torque at any cross section in terms of my displacement, the torsional displacement. Now, I can write down the equation of motion. So, first I will write the moment of inertia of this ring that we have considered. So, this moment of inertia of the ring is mass of the ring times the radius square. So, mass of this ring can be written as rho times dA is the mass per unit length into delta x, that is the mass of this ring, times r square. So, this if I integrate over the full area, then I get the moment of inertia of this element that we are considering. So, this is the moment of inertia times the angular acceleration, which is the double time derivative of our field variable phi, and that must be equal to the balance of torques. And we already have this expression of moment of the torque on any face here. So, I can write this as now, if I divide this whole equation by delta x and take the limit delta x tends to 0, and if I identify this r square dA integral, rho can come out of this integral. So, r square dA integral over the face is once again the polar moment of the area. So, I can write rho I p, the angular acceleration must be equal to and that gives us upon rearrangement the equation of motion of torsional dynamics of a bar, a circular bar. Now, let us look at some examples. So, if you have say a uniform bar, then the equation of motion once again simplifies to rho I p phi t t minus g I p phi x x equal to 0. Now, the boundary conditions for this problem, which will complete the description of the physical situation. So, here this bar is connected to the wall, and therefore, this end of the bar cannot have any rotation. So, this again is a geometric boundary condition. On this end of the bar, the torque is 0, which is therefore given by so this is a geometric boundary condition, whereas this is a on the right end of the bar we have a natural boundary condition. So, with this we complete our discussions on axial and torsional vibrations of bars. Now, to summarize, we have considered axial vibrations of bars, we have derived the equations of motion, and we have seen the boundary conditions of two types, namely the geometric boundary condition and the natural boundary condition. Then we have also derived the equation for a bar interacting with a discrete system, and then finally we have looked at the dynamics of torsional vibrations of circular bars, and we have derived the equation of motion and the boundary conditions. So, with that we end this lecture.